Hello and welcome back to Introductory Astronomy. Last time we talked a little bit about the structure of the Milky Way galaxy, and today we're going to talk about how it formed. Now, any theory of galaxy formation should be able to account for all the properties that we actually observe. For example, the galactic disk is highly flattened, but the galactic halo is roughly spherical. The galactic bulge is somewhat flattened and elongated in the plane of the disk. The galactic disk contains both young and old stars, contains gas and dust, and is a site of ongoing star formation. The galactic halo contains only old stars, no gas and dust, and no star formation during the last 10 billion years. The galactic bulge contains both young and old stars, more old stars at greater distances from the center, contains gas and dust especially in the inner regions, and there is ongoing star formation in their inner regions. The galactic disk has spiral arms. It has an overall white coloration with bluish spiral arms, and gas and stars move in circular orbits in the galactic plane. The galactic halo has no obvious substructure. It is reddish in color, and the stars there have random orbits in 3 dimensions. Galactic bulge, its central regions are probably elongated into a bar. There is a ring of gas and dust near the center. It is yellow-whitish in color, and the stars have random orbits, but some net rotation about the galactic center does exist. So any kind of galaxy formation theory that we come up with has to be able to explain all these properties. The formation of the galaxy is currently believed to be similar to the formation of the solar system, but on a much larger scale. In frame A here, we see how our galaxy possibly formed through the merger of several smaller systems. In frame B, astronomers reasoned that early on our galaxy was irregularly shaped, with gas distributed throughout its volume. When stars formed during this stage, there was no preferred direction in which they moved, and no preferred location in which they were found. Their orbits carried them throughout an extended 3-dimensional volume surrounding the newborn galaxy. In frame C, in time, the gas and dust fell to the galactic plane and formed a spinning disk. The stars that had already formed were left behind in the halo. And frame D, we see new stars forming in the disk that inherit the overall rotation and so orbit the galactic center on ordered circular orbits. All right, but how did the spiral arms form? Measurement of the position and motion of gas clouds shows us that the Milky Way has a spiral form. This is an artist's conception of our galaxy seen face on. Now, this illustration is based on data accumulated by many teams of astronomers during the past few decades, including radio and infrared maps of stars, gas and dust in the galactic disk. Painted from the perspective of an observer 100 kiloparsecs above the galactic plane, the spiral arms are at their best determined positions, apparently emanating from a bar whose length is twice its width. All the features are drawn to scale, except for the oversized yellow dot near the top, which represents our Sun. The 2 small blotches to the left are dwarf galaxies called the Magellanic Clouds. We will talk about them more in Chapter 24. The disk of our galaxy rotates differentially. Stars close to the galactic center take less time to orbit the center than those further out. The white arrows represent angular speed of the disk. The big red arrows denote time evolution from left to right. If spiral arms were somehow tied to the material of the galactic disk, this differential rotation would cause the spiral pattern to wind up and disappear in a few 100 million years. Spiral arms would be too short-lived to be consistent with the numbers of spiral galaxies we observe today. The origin of the spiral arms is still a mystery, but there are two theories. Theory 1. Spiral arms appear to be density waves, with stars moving in and out of them, such as cars move in and out of a traffic jam. This density wave theory says that the spiral arms seen in our own and many other galaxies are waves of gas compression and star formation moving through the material of the galactic disk. In the painting at right, gas motion is indicated by red arrows and arm motion by white arrows. Gas enters an arm from behind, is compressed, and forms stars. The spiral pattern is delineated by dust lanes, regions of high gas density, and newly formed O and B type stars. The inset at left shows the actual spiral galaxy NGC 1566, which displays many of the features just described. The persistence of the spiral arms as density waves, rather than as structures made up of particular stars, may be understood using a traffic jam as an analogy. The jam persists even though particular cars move in and out of it, and it can persist long after the event that triggered it is over. So let's take a closer look at this picture. Envision a traffic jam on a highway triggered by the presence of a repair crew moving slowly down the road. As cars approach the crew, they slow down temporarily. Then they speed up again as they pass the work site and continue on their way. The result, as might be reported by a high-flying traffic helicopter, is a region of high traffic density concentrated around the location of the work crew and moving with it. An observer on the side of the road, however, sees that the jam never contains the same cars for very long. Cars constantly catch up to the bottleneck, move slowly through it, and then speed up again, only to be replaced by more cars arriving from behind. The traffic jam is analogous to the region of high stellar density in a galactic spiral arm. Just as the traffic density wave is not tied to any particular group of cars, the spiral arms are not attached to any particular piece of disk material. Stars and gas enter a spiral arm, slow down for a while, then continue on their orbits around the galactic center. The result is a moving region of high stellar and gas density involving different parts of the disk at different times. Notice also that just as in our galaxy, the wave moves more slowly than and independently of the overall traffic flow. Theory 2. As clouds of gas and dust move through the spiral arms, the increased density triggers star formation. This may contribute to propagation of the arms. In this theory of the formation of spiral arms, the shock waves produced by the formation and later evolution of a group of stars provide the trigger for new rounds of star formation. Supernova explosions are used to illustrate the point here, but the formation of emission nebulae and planetary nebulae is also important. One thing I would like to note is that this theory can produce only pieces of spirals, as are seen in some galaxies. It apparently cannot produce the galaxy-wide spiral arms seen in other galaxies and present in our own. it may well be that there is more than one process at work in the spectacular spiral arms that we see. So what is the mass of the Milky Way galaxy? The orbital speed of a star or gas cloud moving around the galactic center is determined only by the mass of the galaxy lying inside the orbit, shown here within the gray shaded sphere. Thus, to measure the galaxy's total mass, we must look for objects orbiting at large distances from the center. If the matter in the galaxy ended abruptly at 15 kiloparsecs, which is the edge of known spiral and globular cluster distribution, the velocity of an object beyond that edge should diminish with distance, as the dashed curve shows below. But it does not. In fact, more than twice the mass of the galaxy would have to be outside the visible part to reproduce the observed curve. So this is the actual rotation curve for the Milky Way galaxy. We have the rotation speed against distance from the galactic center. The fact that the red curve does not follow the dashed line, but instead stays well above it, indicates that additional unseen matter must be beyond that radius. So what could this dark unseen matter be? It is dark at all wavelengths, not just the visible. So it is literally dark for us. Could it be stellar mass black holes? Probably no way enough of them could have been created. Could it be brown dwarfs, faint white dwarfs, and red dwarfs? Currently, this is the best star-like option. How about weird subatomic particles? It could be, although we have no direct evidence so far. A Hubble search for red dwarfs turned up too few to account for dark matter. If enough existed, they should have been detected. Here you see a sensitive visible light observation with the Hubble Space Telescope that have ruled out the faint red dwarf stars as candidates for dark matter. The object here is called the globular cluster 47 Tucani, and it is one of the many regions searched in our galaxy. The inset, which is 0.4 parsecs on a side, is a high-resolution Hubble image of part of the cluster. The red dwarfs that would be expected if they existed in sufficient numbers to account for the dark matter in the galaxy are not found. The red stars that are seen are giants. The bending of space-time can allow a large mass to act as a gravitational lens. Observation of such events suggests that low-mass white dwarfs could account for as much as 20% of the mass that is needed. The rest is still a mystery. Taking a look at frame A, we have gravitational lensing by a faint foreground object such as a brown dwarf, which temporarily causes a background star to brighten significantly, providing a means of detecting otherwise invisible stellar dark matter. Frame B is a brightening of a star during a lensing event, this one implying that a massive but unseen object passed in front of the unnamed star at the center of the two boxes imaged 6 months ago. This is a view toward the galactic center in visible light. The two arrows in the inset indicate the location of the center. It is entirely obscured by dust. Because of this heavy obscuration, even the largest optical telescopes can see no further than 1/10 the distance to the center. To connect with previous figures, the M8 nebula can be seen at extreme top center. You can look at section 18.2 in your textbook. The field is roughly 10 degrees vertically across and is a continuation of the bottom part of figure 18.5. The overlaid box outlines the location of the center of our galaxy. The inset at right shows an adaptive optics infrared view of the dense stellar cluster surrounding the galactic center, whose very core is indicated by the twin yellow arrows. Let's take a closer look at the galactic center. In frame A, we have an infrared image of part of the galactic plane that shows many bright stars packed into a relatively small volume surrounding the galactic center, indicated by a white box. The average density of matter in this box region is estimated to be about 1 million times that in the solar neighborhood. Frame B. The central portion of our galaxy as observed in the radio part of the spectrum. This image shows a region about 100 parsecs across surrounding the galactic center, which lies within the bright blob at the bottom right. The long wavelength radio emission cuts through the galaxy's dust, providing a view of matter in the immediate vicinity of the galaxy's center. Frame C is a recent Chandra image showing the relation of a hot supernova remnant in red and Sagittarius A star, the suspected black hole at the very center of our galaxy. Frame D is a spiral pattern of radio emission arising from Sag A star itself, which suggests a rotating ring of matter only a few parsecs across. All images are false color since they lie outside the visible spectrum. Sag A star is the suspected black hole at the very center of our galaxy. The galactic center overall appears to have a stellar density 1 million times higher than the Earth's, a ring of molecular gas that is 400 parsecs across, very strong magnetic fields, a rotating ring or disk of matter a few parsecs across, and a strong X-ray source at the center. So there is an enormous black hole at the center of the galaxy, which is the source of this phenomena. An accretion disk surrounding the black hole emits these enormous amounts of radiation. Let's take a look at the pictures right here. This is an extremely close-up map of the galactic center on the left, which was obtained by infrared adaptive optics, resulting in an ultra-high resolution image of the innermost 0.1 parsec of the Milky Way. The resolution is high enough that the orbits of individual stars can be tracked with confidence around a still unseen Sagittarius A star marked with a cross. The inset shows the orbit of the innermost star in the frame, labeled S2, between the years of 1992 and 2003. The solid line shows the best fitting orbit for S2 around a black hole of 3.7 million solar masses. And here's a brief summary of Chapter 23. A galaxy, stellar and interstellar matter bound by its own gravity. Our own galaxy is a spiral. Variable stars can be used for distance measurement through the period luminosity relationship. The true extent of the galaxy can be mapped out using globular clusters. Star formation occurs in the disk, but not in the halo or bulge. Spiral arms may be density waves. The galactic rotation curve shows large amounts of undetectable mass at large radii, which we call dark matter. Activity near the galactic center suggests the presence of a 2 to 3 million solar mass black hole. Please study chapter 23.4 through 23.7 and be able to discuss possible explanations of the existence of spiral arms in galaxies, explain the possible nature of dark matter, and some of the phenomena observed at the center of our galaxy. Until next time.